Alright, good morning and hello class. So last week we looked at exponential equations. Today we're going to start looking at logarithmic equations. So make sure you receive a copy of the notes. It should look just like this. So go ahead and pass those around the classroom and you can go ahead and take today's notes on the handout. We'll be starting off on example 13. So go ahead and pull that on out. And we'll go ahead and get started. If necessary, pause the video. Do not continue playing until everybody's received this handout so we can start taking notes. Now that you've received it, so one type of logarithmic equation we're going to look at is when you have two logarithmic expressions set equal to each other, and they have to be of the same base. Since logarithms are one-to-one, we can solve in the following fashion. We essentially set the equation log equal to log, and then we can just drop the logs. So if log base 19 of negative 5b equals log base 19 of the quantity 9 minus 2b, that can only be true if those two equal each other. So you can essentially just drop the two logs. So I'll go ahead and solve this. I'll go ahead and add 2b to both sides. It's going to get me negative 3b when I bring everything down. Divide, and there you have it. B equals negative 3 is my solution. Note here, to log base 6 equal to log base 6 if log equals log, since it's a one-to-one function. Since the outputs match, the inputs must also match. In other words, 7 minus 5n equals 2n. And I'll go ahead and add 5n to both sides. Divide, and done. Cool. So nice little property of logarithms. So I want you guys to go ahead and pause the video and attempt problem 15 on your own. So it's going to be setting these two equal to each other and solving that linear equation. Go ahead and pause the video, try it on your own. Once everybody has finished the problem, go ahead and continue playing. Alright, so hopefully everybody has attempted problem 15. Again, I want you to attempt it on your own, and now I'll go ahead and go through it. So you have 2b plus 4 equals 5b plus 7. And then just go ahead and solve the equation. So I'll subtract 2b from both sides, subtract 7 from both sides. I'll do two steps here. It's going to give me negative 3 equals 3b, b equals negative 1. So if you got negative 1 as your answer, excellent work. Now, 16 will take a little bit more of a manipulation. Note that the logarithms are not set equal to each other. But I can add anything I want so long as I add it to both sides. So I'm going to move that logarithm from the left-hand side to the right-hand side of the equal sign. So that'll get me to log base 4 of 13 equals log base 4 of 2x minus 4. So the only way this could be a true statement is if 2x minus 4 equals 13. And that's essentially our equation. Alright, then you just go ahead and add 4 to both sides. And then I'll go ahead and divide it by 2. And there's my solution. Alright, cool. So last two examples are going to be quadratic. Now, one thing I want to mention before I proceed, if you look at the directions here, the steps is check for extraneous solutions. Remember, you can't have negatives inside of a logarithm. So if I plug a negative 3 back in, that'll become positive, which is fine. If I plug in 1 here, that's fine. If I plug negative 1 in here, it'll be fine. 17 over 2 will be fine. Let me actually double check that. 17 over 2. So 17 divided by 2 is going to be... Yeah, that'll be fine. It'll be more than 4. You multiply it. Now let's go to look at these equations. So same strategy applies as the previous. We're going to use that one-to-one property, so these two have to equal each other since they're both the same base. So p squared minus 4p equals 40 plus 2p. Now what makes this example drastically different from the previous is notice we have a quadratic equation. Note the variable squared. So typically when we're solving quadratics, we're most frequently going to set them to 0. So go ahead and set the equation equal to 0. So I'm going to subtract this 2p from both sides. So subtract 2p from both sides. That gives me negative 6p. And I'll subtract this 40 over. So we'll go ahead and set it to 0. I'm going to pause here for a brief moment. If necessary, pause the video, try it on your own. All we're doing is setting everything to 0, getting everything on one side, and now we're going to go ahead and factor. So remember, to factor an a equals 1 quadratic trinomial, I want two numbers that multiply to c and add up to b. In other words, two numbers that multiply to negative 40 and add up to negative 6. So let's think what multiplies to 40. 8 and 5 do, but those don't add up. 4 and 10 will do the trick. So let's see here. Yep. Notice when I add them up, negative 10 plus 4 equals negative 6. And when I multiply them, I get negative 40. You could FOIL this to verify. You know, it's just solving quadratics. You know, you all have seen it before and solved numerous quadratics at this point. And if two numbers multiply to 0, either the first one equals 0, so p equals 10, because 10 minus 10 would equal 0, true statement, or negative 4. Now the negative 4 will work. If I plug it in, I don't get negative inside the logarithm. I'd get 16 plus 16, which is fine. And then 40 minus 8, which is fine. And then the 10 would work just fine. So this will have two solutions. Let's go ahead and look at this example 18 before we flip on over. So again, one-to-one functions. So the inputs must be equivalent. Note the variable squared. So that what that tells us is we're going to have another quadratic. So I'm going to go ahead and set it to 0. I'm going to add 3x to both sides. So plus 3x cancels on the right. Negative 11 plus 3, you can use your calculator if you want. It'll be minus 8x. And then subtract the 20 over. And we're going to go ahead and solve it from there. So give me one moment here. All right. So we want to try and find two numbers that multiply to negative 20 and add up to negative 8. I can't think of any two numbers. Oh, actually, 2 and 10. 2 and 10 will do the trick. I was about to run the quadratic formula, but it's okay. So subtract 10, add 2. That'll combine to negative 8 and multiply to negative 20. And that's going to get us x equals 10. Or x equals negative 2. Now if we take a look at the 10, notice when I take 10 and plug it in, I'm going to get 100 minus 110, which is negative. So that 10 will not work. That's going to cause a negative inside the logarithm. All right, another way of looking at it, if I plug in 10 here, I get 20 minus 30, which is no good. Now let's test out the negative 2. If I plug in negative 2, I'm going to get 4 plus 22, which is fine. And here I'll get 20 plus 6, which is fine. So just be careful. Remember, your solutions cannot cause negative inside the logarithm if you were to plug them back in. So you want to double check that. So let's go ahead and flip on to the back side. We're going to look at some different types of equations. So flip your page on over. So these equations on the back side are what we do if the equation is of the form log equal to a number. So what we want to do is condense to one single logarithm, set it equal to a constant, and switch it to an exponential. So, for example, we have log base 3 of x minus 5 equals 2, so we want to switch this to an exponential. So you had to do this in your last exam. So quick little recap, a base 3 logarithm can be switched to a base 3 exponential. And remember, when you switch back and forth, you're going to swap the inputs and outputs. So when I switch it to an exponential, I'm going to get 3 squared equals x minus 5. The old output of the logarithm becomes the new input of the corresponding exponential. The old input of the logarithm becomes the new output of the corresponding exponential. Basically, your inputs and outputs get flipped. You go ahead and solve this. So 3 squared is just 9. Add 5 to both sides. And there's our solution. And notice 14 is okay. If I plug it into the logarithm, it'll work out just fine. Now here, we can't set the logarithms equal to each other because I got this extra constant. But what I can do is combine these logarithms. So remember, we went over this last week, actually more than a week ago in class. Subtraction of logarithms translates into a division property. So this goes back to that homework assignment you did when you were combining logarithms. So subtraction translates into division. So I can go ahead and simplify that. It's 45 divided by 3 is 15. Now switch it to an exponential. Remember, for our common logarithm, it's base 10. And then swap the inputs and outputs. These get flipped to opposite sides of the equal sign. So I have 10 to the first power equals 15x. Therefore, x equals 10 over 15. I guess I should reduce that. So 2/3. X equals 2/3. Let's go take a look at the next one. So here, we're ready to switch it. So no logarithms to combine here. Base 4 logarithm can be switched to a base 4 exponential. And here's the important part. I want you to pay attention. We're going to swap the input and output. So the 7 is going to come to the new exponent, and the x squared is going to get isolated. Now let's see here. 4 to the 7 is going to be a large value. So 4 to the 7th power is 16,384. All right. And then I'm going to go ahead and square root both sides to get rid of the squaring. Just remember, when you square root both sides, going back to previous lectures, you need a plus or minus sign. Now we get 128. So x equals plus or minus 128. And there we have it. Looking at the next equation, I can't set log equal to log because I got a third non-zero term, but what I can do is combine these. Remember, addition translates into multiplication, so we went over that about a week and a half ago. And now we can go ahead and switch it. So remember, adding logarithms, they can be combined via a multiplicative property. So now that I switch, it's time for the key step, time to switch it. It's a base 10 logarithm, which I can change to a base 10 exponential, and these two sides, these two expressions are going to get flipped when I switch it. So it'll be 10 to the first power equals x times x plus 9. We'll go ahead and distribute. Again, I want to pause here for a brief second. These are key steps. Base 10, swap the input and output. So I got 10 equals x squared plus 9x. Let's go ahead and set it to 0. Subtracting the 10 on over, we can factor that to x plus 10, x minus 1. We get negative 10 and positive 1 as our two potential solutions. Now notice when I go to plug these back into the original equation, if I plug in negative 10, I'm going to get negative inside the logarithm, which is extraneous. Won't work. X equals 1 is the only solution that'll work. So again, combine the logarithms, switch it to an exponential, solve the equation, check for extraneous solutions. Make sure if you plug it back into the original equation, you don't get negative inside the logarithm. Moving right along here. So again, this is going to be more practice with combining logarithms. So let's go ahead and combine these two. Remember, you can pack the coefficient in as an exponent. So I can pack that in as x cubed. And now I can combine those two. Remember, addition of logarithms will translate into multiplication, just like the previous example. And then we can go ahead and switch it. This is a base 10 logarithm, so we'll switch to a base 10 exponential. These two will get flipped. So the 3 is going to come over to the right. 8x cubed is going to go over to the left. And then we'll go ahead and solve that equation. So 8x cubed equals 10 cubed is 1,000. So then x cubed equals 1,000 divided by 8, which is 125. And then to get rid of cubing, I'm going to go ahead and do a cube root on both sides, which is the same thing as a power of 1/3. Let me see if this has any. Oh, yep, it does have a cube root. So I'm going to go ahead and take my calculator. If you hit the math button on a TI-84, you can see there's a cube root feature there. So I'm going to do the cube root of 125, which is 5. There's my answer. Notice when I plug it back in, it's positive inside the logarithm, which is fine. Remember, we used a cube root to cancel out the cubing. Let's look at example 24. So I could pack in that coefficient as a power. This is what we were doing about a week and a half ago. So log of x squared minus log of 4 equals 0. I can combine these two logarithms. Remember, when I subtract a logarithm, it's going to translate into a form of division. And then go ahead and switch it. So it's going to be 10 raised to the 0 power equals x squared over 4. Remember, when I switch it, base 10 logarithm will switch to a base 10 exponential and then swap the inputs and outputs. So the x squared over 4 goes to the other side of the equal sign. 0 becomes the new exponent. 10 to the 0 equals 1. Multiply both sides by 4. Again, this is just solving equations. And then square root both sides. Remember, square root property, if I square root both sides, I need a plus or minus. So you get plus or minus 2. And again, all I did there was just square root both sides to cancel out the squaring. Now notice negative 2 will not work because then it'll give me negative inside the logarithm. So positive 2 is the only answer that will work. Let's go to look at these last two examples. They both involve the natural logarithm. Remember, the natural logarithm is a base e logarithm. So natural log of 3x equals 2. Logarithm is already isolated. We can switch it. So base e logarithm will switch to a base e exponential. And then we're going to go ahead and swap them. Remember, when I switch forms, the input is going to become the new output. The old output is going to become the new input when you swap them. And then go ahead and divide by 3. That's e squared divided by 3. And if we want to go ahead and round that to a decimal, we say, okay, e squared is that number divided by 3. It's about 2.46. Roughly 2.46. All right, last one. So a couple of things here. I'm going to subtract 7 from both sides to get the logarithm by itself. And I'm going to pack in the coefficient as an exponent. And now that the logarithm is isolated, we can switch it. So we have to isolate that logarithm first. Sometimes you have to combine logarithms. Sometimes you have to move some constants around. But before you switch, you need to get one single logarithm to switch it. It's base e. So that'll change to a base e exponential. Inputs and outputs will get flipped. And there you have it. It's going to be cube root of e to the negative 2 equals x. If we want to, we can go ahead and type that into a calculator. So in the calculator, punch in a cube root of e to the negative 2, which is going to be roughly 0.51 if you wanted a decimal approximation. All right, so that covers this entire page. At this point in time, you will be receiving a homework sheet. This homework assignment is going to be due next class. So it will be due next class. I want you guys to go ahead and use the remainder of the class period to work on the homework sheet. But other than that, have a wonderful day. If you have any questions, feel free to shoot me an email. And keep up the good work.